Welcome to CSC 201, Lesson 8.2, Reflexivity, Symmetry, and Transitivity. All right, let's look at a set A, 2, 3, 4, 6, 7, 9. We're going to define a relation R on A as follows. For every x and y in A, x is related to y if and only if 3 divides the difference x minus y. So let's draw a directed graph of R. So I have my elements would be 4, 7, 2, 3, 6, and 9. Those are the 6 elements in the set. And I drew them the way I drew them just so that my arrow, I don't get a lot of overlapping arrows, but there's nothing incorrect if your arrows overlap. I just wanted to make it clearer. All right, so now I'm going to decide any 2 points are going to be related if their difference is divisible by 3. So let's see, 4 to itself. So the difference of 4 minus 4 is 0, and 0 is divisible by 3. So 4 is related to itself. In fact, everything is related to itself because subtract anything from itself and you get 0, and 3 will divide it. So everything's related to itself. So I'm going to put these little loops on everything here. All right, now 4 and 7. 4 minus 7 is -3, and 3 does divide that, right? -3 is divisible by 3, so I'm going to have an arrow from 4 to 7, and I'm also going to have an arrow from 7 to 4 because 7 minus 4 is 3, which is divisible by 3. Now 4 and 2, the difference between 4 and 2 is 2, and that is not divisible by 3. And 2 minus 4, -2, not divisible by 3. So I'm going to have no arrows between 4 and 2. 4 and 3, their difference is 1 or -1 if you do the other direction, and that is not divisible by 3. 4 and 9, the difference is 5 or -5, no arrows there. And 4 and 6, the difference is 2 or -2, no arrows there. Okay, so that covers 4. How about 7? Is 7 related to 2? Well, the difference here is 5, not divisible by 3. 7 minus 3 is 4, not divisible by 3. 7 minus 9 is -2, not divisible by 3. And 7 minus 6 is 1, not divisible by 3. So we got the 4 and the 7, their arrows are done. 2, if I look at the difference between 2 and every other number, I've got the difference is 2, difference is 5, difference is 1, difference is 7, and the difference is 4. None of those differences are divisible by 3. So 2 done. Now I'll do 3. I already checked 3 with 2, 4, and 7, so I just need to do these 2. Okay, so 3 minus 6 is -3. 6 minus 3 is 3. Both of those are divisible by 3, so I have arrows here like that. And then 3 and 9, the difference between 3 and 9 is -6 or 6, depending on the order. Both of them are divisible by 3. So I've got to put some arrows like this. And then the difference between 9 and 6 is 3 or -3, and both of them are divisible by 3. So put arrows here. All right, so there's my directed graph for this relation. This graph is very special. It has 3 important properties. The first one is called reflexivity, and the way you can see it in the graph is that every single point has a loop on it. Okay, so every x is related to itself. For all x in A, x is related to x. So because we have a loop on every point. Symmetry. In each case where there is an arrow going from one point to a second, there is another arrow going from the second back to the first. So I have 4 to 7 and 7 to 4. 3 to 9 and 9 to 3. I always have these double loops anytime 2 points are connected. Now, if 2 points are not connected, it's vacuously symmetric. So it's just when you have a connection, it has to go both directions for symmetry. So if x is related to y, then y is also related to x. And then finally, transitivity. In each case where there are arrows going from one point to a second and from that second point to a third, there's a third arrow going from the first to the third directly. So if x is related to y and y is related to z, then x is related to z. So let's just trace one out here. So here I have 3 is related to 9. 9 is related to 6. And I can go directly from 3 to 6, right? 3 is also related to 6. So if 3 is related to 9 and 9 is related to 6, then 3 is related to 6. So anytime you can get from one point to another via 2 steps, you should also be able to get there in 1 step. So for example, we have a set A, which is just the set of 4 numbers 0, 1, 2, and 3. And I've defined 3 different sets, R, S, and T on A. So they're just sets of ordered pairs. And I want to figure out, looking at each of these, are they reflexive, symmetric, and or transitive? So let's go one by one, one property at a time. So we'll do all reflexivity for all 3 sets. So for R, to be reflexive, we have to have 0, 0, 1, 1, 2, 2, and 3, 3. Every single point in A has to be related to itself. So R is reflexive. Now is S reflexive? It has 0, 0, but it doesn't have 1, 1, 2, 2, and 3, 3. So not reflexive. And then T doesn't have any of them, not reflexive. All right, let's look at symmetry for the 3 sets. Okay, so symmetry says that if x comma y is in the set, then y comma x has to also be in the set. So 0, 1, if 0, 1's in the set, then 1, 0 would have to also be in the set for symmetry, and it is. Okay. And then also for 0, 3, 3, 0 has to be in the set, and it is. And then 1, 1, 2, 2, and 3, 3. Okay, so those are the only non-symmetric points, and they are all in the set. 0, 1, 1, 0, 0, 3, 3, 0. So it is symmetric. Anytime x is related to y, y is also related to x. Now for transitive, let's do symmetric on the other 2. So for S, 0, 2 is in the set. For it to be symmetric, 2, 0 would have to also be in the set, and it is not. Okay, so we are missing, for example, 2, 0. We would also need 3, 0 and 3, 2 to make that symmetric. But as soon as one is missing, you can say not symmetric. And then for set T, is it symmetric? Well, look at 0, 1. 0, 1 is in the set. For the set to be symmetric, 1, 0 would have to be in the set, and it is not. Also 2, 3. Okay, 2, 3 is in the set. For the set to be symmetric, 3, 2 would also have to be in the set. So here you would need at least 1, 0. And then for transitivity for the 3, all right, so for set R, we need that anytime x comma y and y comma z are in the set, x comma z has to be in the set. So let's see, 0, 1 is in the set, 1, 1 is in the set, and 0, 1 is in the set. So that one's fine. Okay, how about 1, 0 is in the set. 0, 3 is in the set. But 1, 3 is not in the set. Okay, so 1 is related to 0, and 0 is related to 3, but 1 is not related to 3. So that's, for this to be transitive, 1 would have to be related to 3. 1 comma 3 would have to be in the set. So this is not transitive. Okay, set S, 0, 0, 0, 2, 0. Yeah, I think this is transitive. Okay, so we have 0, 2, and 2, 3. So if 0, 2, and 2, 3 are in the set, then 0, 3 would have to be in the set, and it is. So I think that's the only sort of transitive situation, so that one works. And then for T, 0, 1, and 2, 3. So remember, this says that if X is related to Y and Y is related to Z, if that's true, then X has to also be related to Z. But there are no situations where this is true. There is no X is related to Y and Y is related to Z. There's no place where this is true in T. So I have 0 related to 1, but I don't have 1 related to anything. And I have 2 related to 3, but I don't have 3 related to anything. So remember, the only way that an if-then statement can be false is if this is true, but this is false, right? But this is vacuously true. So this is transitive, yes, but it's because the if-then statement is vacuously true. Right? Because even though this is false, like we don't have this situation, false, false for an if-then is true. The only way you can get an if-then to be false is if this is true and this is false. So we have false, false. Okay, which of the following relations satisfy all 3 properties? So equality, is it symmetric, right? If you have any number, is it always equal to itself? Yeah, symmetric. If X is equal to Y, then Y is equal to X. Yeah, if you have 2 numbers that are equal, the order of the equality doesn't matter. And if X equals Y and Y equals Z, then X equals Z. Yes, that is also true for equality. So equality is an equivalence relation. Okay, it satisfies all 3: reflexive, symmetric, and transitive. How about less than? Is X always less than itself? No, right? Unless I did less than or equal to, that's not true. How about X less than Y if and only if Y is less than X? That's definitely not true. They can't both be true. And then how about if X is less than Y and Y is less than Z? Does that mean X has to be less than Z? That is true. So less than is transitive, but it's not symmetric and it's not reflexive. Okay, parallel. Thinking about lines, they told us to assume that a line is considered parallel to itself. So if I have a line L is parallel to L, they said that's true. Okay, they told me to assume that. And if L1 is parallel to L2, is that equivalent to saying that L2 is parallel to L1? Yeah. If 2 lines are parallel, it doesn't matter which one you say first. And then transitive, if L1 is parallel to L2 and L2 is parallel to L3, does that imply that L1 is parallel to L3? So here are 2 lines parallel, L1 and L2. L1's parallel to L2. L2's parallel to L3, so I'll put a third one here, parallel. Yes, it does look like L1 and L3 have to be parallel to each other. All right, and then how about perpendicular? Okay, so if you have two lines, L1 and L2. Well, let's just look at L1 first. Is a line perpendicular to itself? No, a line can't form a 90-degree angle with itself. Now, if L1 is perpendicular to L2, is that logically equivalent to saying L2 is perpendicular to L1? Yeah, two lines are perpendicular. Doesn't matter what order you say them in. And then for transitive, if L1 is perpendicular to L2 and L2 is perpendicular to L3, does that mean that L1 is perpendicular to L3? Well, let's draw a picture. Here's L1. It has to be perpendicular to L2. So there's L2. And L2 has to be perpendicular to L3. So I'll put L3 here perpendicular to L2. Notice L1 and L3 are not perpendicular to each other. They look parallel. So this is not transitive. Perpendicular is not transitive. Okay, so here's sort of a non-mathy example, friendship. So R is a relation on the set of all people such that X is related to Y if and only if X is friends with Y. Okay, so if you have a person, are they automatically friends with themselves? I hope so. Let's optimistically say yes. If you have two people who are friends so that X is friends with Y, does that automatically mean Y is friends with X? I think if we're defining friendship appropriately, then yes, that's true. And then the last one for transitive, if X is friends with Y and Y is friends with Z, does that imply that X is friends with Z? That is not the case. There are plenty of examples where these two people are friends, X and Y are friends, Y and Z are friends, but X and Z don't get along. They don't like each other. They're not friends. So friendship is not transitive.